In my recent videos, you have learned how to differentiate between the sample and the population, choose appropriate notation for given information within the context, and you've been exposed to 3 different confidence interval formulas and 2 tables, the Z table and the T table, in order to find critical values. Finally, in this video, we are putting it all together in order to actually create confidence intervals and learn how to interpret them. This first page of my lecture handout just summarizes the formulas again and when to use the 2 different confidence interval formulas for the mean. And so you see that in the top portion of the table here. When sigma is known, use the formula with sigma in the margin of error, and when sigma isn't known, you estimate it from the sample and use change Z to T, and that's the second formula here. And remember that every confidence interval that you're learning now and that you will learn in a couple of weeks has the same form of a point estimate plus or minus a margin of error. All right, so let's take a look at the first problem here. Now this problem will likely look familiar because it was on the notation lesson. So we've already read through it and we've practiced figuring out what information is given and the appropriate notation for that. And that's step 1, in my opinion, is to read and comprehend what you're reading, figure out what information is given, and assign appropriate notation. So for this problem, feel free to read it again, but there are n equals 30 students. The average IQ of those 30 students was 125. It is well documented, so that's about the population. The population has an IQ of 13, or a standard deviation of IQ of 13.89. The only new piece of information here is at the very end, determine a 95% confidence interval for mu. And so that means that 1 minus alpha, which is your confidence level, that is 0.95. Once you've labeled all that, then you get on to step 2, which is you need to figure out, are you going to use the Z or the T version? Because sigma is known, you're going to be using Z, and then use the Z table in order to find the appropriate critical values, which for a 95% confidence interval, we actually did in one of the recent videos. And so that was plus or minus 1.96. Once you have all this information, then you're ready to actually plug in to the confidence interval formula and determine the 2 bounds. So there is the formula rewritten over again. The mean is 125, critical value is 1.96. It's not necessary to write it as a minus or positive, just plus or minus, because that's part of the formula. And you've got sigma of 13.89 over the square root of 30. When you do 125 minus the right side, you get 120.03, and 125 plus the right side gives you 129.97. Now, often students will ask, how many decimal places do I want? And doing it depends what you're going for, but in this case, since 13.89 has the most decimals, I tend to go for 2. That's just one of my reasonings. But if you had gone 1 decimal place, that would be fine also. Truncating to none is a little much, but I wouldn't take much off for that. Finally, what we end on is interpreting this. So what does this interval mean? And there's a few parts that I'm looking for. What I want are, for the first part that I've written in black here, is state how confident you are. This was a 95% confidence interval, and so we are 95% confident. Then say what we are confident about. And so this is describing the parameter in context, and the parameter is mu. That's why I've circled inside the interval. And that is the population mean IQ of high school calculus students. So we are 95% confident that the mean IQ of high school calculus students is. And the last part is state your bounds. Where is that value likely to be? It is between 120.03 and 129.97. So it's not hard. I do see that it's very algorithmic in that I'm looking for 3 parts. How confident are you? what does mu or p, if that's your parameter, mean in context, and then where does that value likely lie. Let's jump to problem 3 just to see another example. And so this is another one that may look somewhat familiar. A principal administered IQ test to 20 randomly selected students. Among the sampled students, a mean and a standard deviation was observed. Determine a 99% confidence interval for the mean IQ. And so in this case, again, you want to write down what you know. What we know is that n is 20, x bar is 108, s is 5. It's s because that 5 value came from the sample. That's the second sentence. 1 minus alpha is given to be 0.99 or 99%. And since s is known, we are going to be using the t-table. And you should get 2.861 plus or minus, and that's based on 19 degrees of freedom. Remember, degrees of freedom for now is going to be n minus 1, so one lesser sample size. So make sure that you're able to find this value in the t-table. In step 3, we want to compute the bounds, which we've got here. And so the formula again is rewritten on top. You plug in x bar is 108, t star, the critical value is 2.861, s is 5, and n is 20. And when you calculate, you get mu is between 104.8 and 111.2. So in this case, since all of our information other than the critical value was integer valued, I decided to have at least one decimal. And so that's how I got and stayed my interval. So what does it mean? Now we want to interpret. So we are 99% confident that the mean IQ of students at the school, that's your population, is between the values that I said before, 104.8 and 111.2. Again, those are the 3 components that I'm looking for when interpreting any confidence interval. So 1 had the population standard deviation, 3 did not. So they had to give you S, which they did. Let's take a look at 5. A coin is tossed 10,000 times and the number of heads is recorded. This is a new problem. I didn't have this one in the notation video. It is found that the number of heads is 5,167. Is this a fair coin? Prove with a confidence interval. Now, this problem asked for a confidence interval, but they didn't give you a confidence level. When that happens, the default is 0.95. So when confidence level isn't given, let 1 minus alpha be 0.95. But other than that, you might go through this problem and you say, okay, well, there were 10,000 tosses, so that's my n. I don't see an x bar. Could I get maybe a p hat? And it looks like we can. You could get the proportion of heads that was observed in the 10,000 tosses. And so that's going to be 5,167 out of 10,000, which is 0.5167. So for this problem, we can get a confidence interval, but it's going to be for p, not mu, like the first 2 examples. Now that we have gotten all the information we can from this, in addition to the fact that 1 minus alpha is going to be 0.95, we're going to need our critical value, which you've seen before, 1.96. And then we could plug in to the appropriate formula, which, just scrolling back up here, that's going to be the p hat. I'm looking at the 3rd line in the table, p hat plus or minus the margin of error, z star times the square root of p hat q hat over n. So that's the one I'm going to be using. And when you do that, what happens? Well, remember that if p hat is 0.5167, q hat is 1 minus that. So that gives you 0.4833, which you see in the top right of the square root term. And when you compute this, you get P is between two values. So now when we're dealing with proportions, percentage, probabilities, I typically go 4 decimal places. And so that's what I did here. And I do that just because your tables with probabilities have probabilities typically to about 4 decimal places. And so that's kind of my philosophy. Notice that I have P in the middle, not P hat. So P is somewhere between 0.5069 and 0.5265. So finally, we need to interpret this. Now remember, our goal for this problem is to figure out, is this a fair coin? And so based on the interval, we are 95% confident that P, which is the true proportion of heads or probability of heads for this coin, is a value between 0.5069 and 0.5265. So is this a fair coin? Well, if it's fair, what can P be? Or what should P be able to be? Well, obviously I can't hear anyone, but hopefully you said or are thinking 0.5. So with that in mind, can P be 0.5 according to this interval? And your answer hopefully is no. 0.5 is close, but it is not inside the interval. And that's exactly the reasoning we're using to answer the question, is this a fair coin? Since 0.5 is not in the interval, the coin is not fair, it's unfair, it's biased. Any of those phrases are fine. And so that's what I'd be looking for is what's your answer and justify it. With that, there were 2 problems that I skipped over, problems 2 and 4. So pause the video, give it a shot to try to find confidence intervals and interpret them for those. And when you are ready, feel free to start the video back up. All right, so I trust that you have attempted both problems, numbers 2 and 4. So let's go over them and you can check yourself. Men tend to sleep an average of 7 hours a night. Past research has found that the number of hours women sleep each night has a standard deviation of 1.5 hours. A sleep study recorded the number of hours that each of 50 females slept in a night and found that on average they slept 9 hours. Is this sufficient evidence to say that females sleep more than males? Support your answer with a 99% confidence interval. All right, so first step. Did you pull out the important information and label it correctly? You probably got N is 50 correct, and 1 minus alpha is 0.99. Hopefully you said that X bar is 9. That's not usually a big issue, but typically 1.5 is the problem. Now, 1.5 is sigma, not S, and that's because it is in the sentence that says past research has found. So that's broad, it's general, it's like past research, historically, it's well known, it's documented. Again, phrases like that are telling you about the population. Or more logically, if that bugs you, when you are in sentence 2, you don't even know of the sample yet. You haven't been told of the 50 females until the next sentence. And so logically, it's not in a reasonable order to associate with the sample. All right, so since sigma is known, if you got that, you should have chosen to use the Z table, which means that you'd get a critical value of 2.575 or something really close to that, 2.57, 2.58. If you happen to have looked up online, you'd find that the exact value is 2.576, but I'm not picky about that detail. As long as it's, you know, something like one of those 3 or 4. All right, so now that you've got everything you need, you plug into the appropriate confidence interval formula, calculate your bounds, and you should get mu is somewhere between 8.45 and 9.55. What does that mean? Now, this is the part oftentimes students don't like doing, but it's good practice to try to interpret. Don't just wait for the answer. And so we are 99% confident, that's step 1, that the average or mean number of hours that females sleep per night, that's part 2. That's what mu represents. is between 8.45 and 9.55 hours. Now, the question that we want to answer, that is the interpretation, but is this evidence that females sleep more than males? And so there's a detail in here which may have bugged you, and that's the number 7. You might have felt like, oh, it's got to be something. And what that is your average hours that males sleep in a night. And so you ask yourself, well, is mu, whatever value mu is, likely to be greater than 7? And since this interval, whatever value mu might be in that interval, is greater than 7, that is the justification to say that there is evidence that females sleep on average more than males. So not too bad, pretty logical. Then there was problem number 4, which was the second one for you to attempt. So let me scroll down to that. A study was conducted to determine, there we go. A study was conducted to determine whether obesity among males is a major issue in the United States. A sample of 100 male subjects in the US was obtained, and each subject's weight was recorded. A male is considered obese if he weighs more than 170 pounds. The mean weight of subjects in the study was 175, and 25 of them were clinically obese. Based on this information, find an appropriate 99% confidence interval for the percentage of American males that are obese. Again, step 1, find the important information. Now, I've circled and highlighted the word percentage because that tells me that this is an inference or an interval for P, which means we need to get or create a P hat. And so I see that in the second sentence, N is 100. In the fourth sentence, I could see that the X bar or average of the sample is 175. Doesn't really matter because we need an inference or an interval for P. But 25 of the subjects were clinically obese. So if I'm letting P hat be the sample proportion that were obese, that's going to be 25 out of the 100 or 0.25. And 1 minus alpha is given in the last sentence, that is 0.99. So there is our summary. We've got P hat, we can get Q hat, which is just 1 minus, so that's going to be 0.75. We have N. We know that for a 99% confidence interval for the Z table, it's going to be 2.575. So we can plug in and get our interval to be P between 0.1385 and 0.3615. Again, we want to interpret that. So we are 99% confident that the proportion of obese American males is somewhere between 0.1385 and 0.3615. That's essentially what I say here for our interpretation. Hopefully you did well or got pretty far along. If not, I'd like to think that this might have clarified some of the misconceptions. It is going to be important. We're in statistical inference now for this course, which is the bulk of the class. And so if you find that you're struggling, please come see me sooner than later. Otherwise, good luck, enjoy the homework and the worksheet, and I will see you later.